I assume everybody has looked at the hat riddle. So because everyone has looked at the hat riddle, there's no need, but it's just so fun I will state it again. So hat riddle. So we have 100 mathematicians. What does that mean? What can you assume about these people since they're mathematicians? They're really smart, right? Let me see, is this tracking? Is it tracking now? It is not tracking. They're all really smart. So if there is something logical that can be deduced, they will deduce it. Like how to fix this? Well, at least it's recording, okay? So, in terms of, the greater scheme of things, it's at least recording. All right. Is my green light on? This is a wonderful thing to be seeing. All right. So if there is something that can be deduced, they will deduce. There is one evil Sith Lord. And places hats on them. And then this is about the level of my artistic ability. All right, so we have our people like this, and then we have a huge number of hats. We have 100 white hats. Oh, we always have this problem. Which do you want the white hats to be? They're filled in or not filled in? Filled in. All right, 100 white and 100 black hats. So what this means is the evil Sith Lord can place whatever hat color he or she desires on each mathematician. Okay? There's 100 people. There's 100 people. They're all in a line. You can only see the people in front of you. Okay? Only see people in front. And you see all of them. Okay. Out of curiosity, has anybody heard of this riddle before today? All right, some people have heard this one. All right, so I want to do this in stages. So the mathematicians strategize beforehand, and they try to come up with what is the best strategy to use to maximize the number of people who correctly state their hat color. And the way it's going to go is you're going to speak in order going down the line, and you must speak in 1 second increments. Now, if there's any calculations that need to be done, they can do it in less than a second because they are mathematicians. So why am I not allowing you to have a variable speaking time?
You can't put in tricks.
You can't put in tricks. I will speak instantaneously if it's all whites in front of me. I will speak with 1/1,000,000th of a second delay if it's all whites and then a black. 2/1,000,000ths of a delay if it's whites, one black, one white after. You can't code all the possibilities like that and have it conveyed by a small delay. Okay? They're speaking at 1 second increments. Yes?
So are we also saying that the guy who can't see anyone else's hat is the guy who has to speak first?
The guy who speaks first is the guy who sees all the stuff in front. So it's the last person speaks first, it goes like this. And so what I want to do is I want to try to attack this problem in stages. So stage 1, can you give me a strategy that will save 50%? So when you speak your hat color, if you say your hat color correctly, your team gets a check. You're safe. If you say the hat color wrong, you lose, your team loses a point. And we want to try to maximize the number of points you gain. If you want to look at it, every person who says the hat color correct, we add $1 million to the pot. Everyone who speaks incorrectly, we subtract $1 million from the pot. Okay? Can you give me a strategy that will do at least 50%?
When you answer incorrectly, does your team know that you answered incorrectly, or do you just get kind of struck down by the Sith?
You get struck down by the Sith.
Wordlessly?
But you do return more powerful than you could possibly imagine. But that's only in a later riddle, unfortunately. So you will not find out if you are right or wrong until the very end.
So, if you wanted to get 50%, you could just have the first guy say the name of the color of the hat in front of him.
Good. So 50% evens say color of the odd. Was that someone? No. Of the odd in front. Right? So if we do something like that, that will get us 50%. Okay. So the question is, can we do better than 50%? They do. So this is a way to get 50%. Can somebody see, say, maybe 66%? I want to try to do this in stages. So this strategy will get you 50%. So you're at least now indifferent towards the game. But can you do better? Can you actually get 66%? Can you make sure 2 out of every 3 are right? So again, I'm the evil Sith Lord. Oh, sorry, in case you didn't know that. I will hear your strategy session, and if you're going to have all the evens say the color of the hats of the odd people in front of them, I will make sure all the evens have a different hat color than all the odds. So whatever strategy you choose, whenever anything can go wrong, I will make sure it goes wrong. So what could we do to get 66%? Any thoughts? So here we were using the evens to help us with the one immediately in front of us. So I know some of you know the answer to the problem, but can you give me a weaker answer? So what we were doing, we want to say 66%. Before, we had something like this, where this one person was helping us with one person over here. If you want to have 66%, how many people should this be helping us with? 2. Okay. Yes?
You could say if the, like, black, if the 2 people in front of you have the same color hat, and they have different color.
Excellent. So you can say black if the 2 of them have the same color, white if the 2 of them have different colors. And now this person can see the hat color of the person in front of them. So if you know that they have the same hat color, this person immediately knows what color they have, and then this person would then be able to figure that out as well. So what you're doing is you're using the fact that each one of these has a lot of information. When we're done with this problem, I will tell you why I care about this. This problem actually has real-world applications. And it's more than just lining up people to put hats on them. So this gets us 66%. What do you think the next thing to try to do? So could we get 75? Is there a way maybe to have one person and to have 3 people here? Or there could be another way to get 75. This is one person trying to help 3. How else could we try to do 75? 2 people helping 6. Yeah. 1, 2, 3, 4, 5. So can you think of any way to have one person help 3? They've got to say something so that they immediately know. So this person can tell if these 2 have the same or different. But this person can't freely speak because this person needs to get their own hat color. So again, with riddles like this, I like to just try to analyze and see how far can we push methods like this. If I was going to try to have this one person help, now over here, this person did freely speak, and then that helped this person over here. So maybe there is a way to make this work. So we have either 0 black hats, 1, 2, or 3. This person might not know which hat is the most popular color. Right? Because these 2 hats could be tied. And so if this person just says which hat is the most popular color, does that help us?
Could it be that maybe the 2 2 out of 6, 2 helping the 6. One says like black if they're an equal number of black and white, and the other one says white if there's one more than the other, and then the second person, if there's one more than the other, says which one it is.
But over here could be more than just one more. And I mean, the difference could be as much as 3. I believe there is a way to get 80% or something like that. So 75% I don't know, but I think you can do 80%. So how might we try to do 80%? So what are the possibilities for these two? So how do we get information over here? This person told us black if they were the same or white if they were opposite. So this is either same or opposite. If they know if they're the same or the opposite, can they each figure out which one what they have? Similarly over here, these are either the same or the opposite. Right?
So then you could go one level up and say if those groups of 2 are the same or opposite?
Ah, so this one will say white if both groups are the same. Oh, no, I'm sorry, I guess black if both groups are the same, and white if both, if the groups are opposite.
There's more than one way they cannot be the same.
So by being opposite, this means same opposite or opposite same. And here, this means same same or opposite opposite. So let's say you speak white, and you know both groups are opposite. Over here, I see both of them have the same hat color. So I now know we have different hat colors. And when these people hear that we've said 2 different hat colors, they'll know we were opposite, so they must be same. I think this works, and I think this gives you 80%. Could we go higher? So I'll leave this as an exercise to see, could you take this up one more level? There is a better approach to this problem. So does anybody know the better approach? There's the one-line answer. So does anybody know the one-line answer to this? So if you think about what's going on, the idea behind the one-line answer is very similar to an idea we've seen several times in other problems. It's this idea of parity. So when we're looking at the checkerboard problems, we could often prove something couldn't be done because of evenness or oddness. And so when we look at the last person sees 99 hats. But it's more than just the last person sees 99 hats. The second to last sees 98. The third to last sees 97. They all have a lot of information. All I need to do is give a small bit of extra information so that they can start computing. So the reason I care about this is, to me, this is very similar to how streaming video works. Is there anybody here who has not watched streaming video at some point in their life? I think by now it's safe to assume everybody has watched some kind of streaming video. If nothing else, maybe you missed one of the classes. How does streaming video work? Do they send you every single pixel and tell you how each pixel changes over time? That's expensive. So if you want to know more about this, I can give you some videos to watch from my operations research class. What you do is you have a powerful computer at both ends, and you transmit a small amount of information that allows you to reconstruct the pictures with high degrees of accuracy. So rather than sending every pixel, you might just say, Fourier expand, or maybe do a wavelet expansion and send a couple of coefficients and then have the computer at the other end build this up. The reason you can do this is you have powerful computers on both ends. You don't have to send every pixel. If you could send every pixel, that's one way to do streaming video. But the bandwidth requirements would be intense. And so instead of what you do is you would often have your red, your green, and blue, I think. You can look at your expansion in red, green, blue space for each pixel. And you'd have a nice function in 2 dimensions. And then you would send the coefficients of your red function, your coefficients of your green function, the coefficients of your blue function, and then build up the image on the other end. So you basically send sort of like a Taylor series expansion, but rather than using 1x, x squared, 1y, y squared, 1x, y, stuff like that, you would use sines and cosines or other bases of functions. And the idea is you can do this because you have powerful computers on the end. This, in some sense, is very similar to that. It's a waste not to take into account the fact that all of these people have knowledge of what's going on in front of them. So the solution is by parity. And this is a huge concept in a lot of these problems. So last says white if C's, do you prefer even or odd?
Even.
Even. First loud voice wins. C's an even number of white hats. And black if C's an even number of black hats. Can the last person see both an even number of white and an even number of black hats? No. There's 99 hats in front of them. Why can't you see an even number of both? This is elementary number theory. So there's either an even number of whites or an even number of blacks. So now imagine they say white. So there's an even number of white hats. You look at the last person, they speak, and so I will almost surely make sure that they are wearing a black hat. But now imagine the 99th person. They know there's an even number of white hats total, and they can see how many white hats are in front of them. What happens if they see an even number of white hats in front of them? They must have a black hat. What if they see an odd number of white hats in front of them? They must have a white hat. And so what you can do is you have this quantity that's going down. It's the parity of the number of white hats in play. And there's a total number of an even number of white hats. They can see what's in front of them. They can figure out what hat color they have. And they speak, they're correct. Now the person in front of them knows. So let's say it was a white hat. So we start off with even number of white. 99 says white. 98 sees an odd number of white hats. So what does 98 know? I'm sorry? So 98 sees an odd number of white hats in front of them. The last person said there's an even number of white hats overall, and the 99th person said white. So if you're looking at it this way, here's 99. 99 has a white hat. There's an even number of white hats, and this person sees an odd number of white. So what hat color does this person have to have? Has to be black, because they see an odd number of white hats. There was one white hat behind them, so it has to be black. And so I'm not going to go through the rest of the calculation, but the knowledge will just propagate down like this. And at the end of the day, everybody will be right except for the last person. So this is amazing. No matter how evil I try to be, I can listen to all your strategizing. I cannot set it up so that more than one of you will get it wrong. Yes?
Is there an elegant way of solving it if you started off with 99 mathematicians?
So now if you have 99 mathematicians, you could have an even number of both.
Okay.
And so what can we do in that case?
Sacrifice the first one?
Basically, I think that is the best thing you can do. But what would your strategy be? Should it always be, say, white? The person you're going to sacrifice. This is really minor because it's only one person. But if your strategy is to always have that first person just randomly guess white, what will I do? I'll put a black hat. So what should your strategy be?
Do we know that there are going to be exactly 100 black hats and 100 white hats?
Well, there's going to be enough so that anybody can have any color hat. I don't want to run out of hats. So what should you do for that last person who has to be sacrificed? Flip a coin, right? Here, choose some mathematical function, look at its special value, and see if it's an even number. Something strange that I do not know what you're going to do, so it's something random. And you just have that one person guess randomly. And in that situation, there would potentially be two people who would die. There is other ways you can attack this problem. So I'm going to just mention one other solution that I particularly like. It does not do nearly as well as parity, but it does get 100% in the limit. So the first method we had, we got it 50% of the time. Not great, but not horrible. Then we got 66%. Once you break 50%, you should start feeling good about yourself. 75%, we had a little trouble with that, but we got 80%. 80% is not so bad. The next question was, could we go up one more level and do even better? 99 out of 100, well, if we do in general n, we're going to be missing at most 2 out of n, so in the limit, we're getting 100%. There is another way to get 100% in the limit. Any thoughts on another way to get a lot? So let's write the number of white hats as b0 plus b1 times 2 plus b2 times 2 squared plus b3 times 2 cubed plus b4 times 2 to the 4th. How much is 2 to the 4th? So this will allow me to get up to 31 hats, not enough, plus b5, 2 to the 5. That allows me to get up to about 63. Plus b6, 2 to the 6. I can represent any number from now 1 to 120 something. Well, actually from 0. I'm going to write the number of white hats in base 2. And what I will do is I will use the last few people to give me the base 2 expansion of the number of white hats. And so if I do that, I will get 100% in the limit. I'll be missing by maybe the logarithm or twice the logarithm of n, but it will be 100% in the limit. So if you're just carrying in the limit, can you save 100% of the people? This will do it. It's not nearly as good as the parity. But one of the ideas here is to try to emphasize different techniques and to show where these things matter. Streaming video is an extremely important industry. And it all comes down to the fact that you have intelligent computers on both ends. You don't have to send all the information. You can send small amounts of information that is then processed by things later in the network. And that's the main reason why I like this problem. I like the logarithm over here. Base 2, this is a really good thing to keep in mind. Representing numbers in base 2, it's a good technique. OK, if there aren't any more comments on this, I want to go to one of the problems we were discussing last time. This was the flipping. OK, is everybody comfortable with this? All right. The flipping doesn't seem to be, not flipping, I guess the pivoting doesn't seem to be working. So what I will try to do is just keep it stable. All right. It's at least recording, so we're making some progress. OK. So the rule is I take the numbers 1 through n, I put them in some order, and if the first number is not a 1, I flip all the numbers. And I keep doing this until eventually a 1 ends up at the top. And that's the claim, is that 1 will eventually end up on the top. Once 1 ends up on the top, I flip the first 1 number. OK, I'm now stuck. This is from the unit on monoinvariants. So what do you think is going to be useful for this problem? Yeah, I have no idea how to do this with monoinvariants. So one idea for something like this, when you have a problem like this, so I'll state it. So 1, 2.n random order if first number k switch order of the first k. So for example, if we were 2, 4, 3, 1, 5, this would go to, I have 2, so I would flip, I would get 4, 2, 3, 1, 5. Now I flip the first 4, and I would get 1, 3, 2, 4, 5. So it's possible that induction might be the way to go, yes?
What do you mean by flip? Is it any randomness or?
No, it's not any random. It's flip, so you take the first k, and then you run them backwards. So here I'm flipping this box, here I'm flipping this box. Now instead of going 4, 2, 3, 1, I'm going 1, 3, 2, 4. So run backwards. What is the hardest part of any monoinvariant problem? Finding the monoinvariant. What are candidates? Yeah, this is where it would be really nice if things could flip and swivel, but what would be candidates? I don't care if they work yet. What would be a possible candidate for a monoinvariant? Yes? Okay. A number other than 1 is only in the first position at most one time. And if that were the case, you could keep track of how many numbers have been in the first position, and eventually a 1 would have to get into that position. That would be a great monoinvariant. And we would just keep track of how many numbers have been first. What else could we do? The number 1 never goes lower after a flip. Imagine that were the case. If 1 never gets to a lower position, then we would eventually win. Right? Or would we win? Maybe 1 is staying always at a given place. So this would almost surely not be enough. It's also false.
You got like 4, 1.
So you could have 4, 1. So if we do, I can't do that now. So if we did 4, 1, 2, 3, 5, then when we flip this, it would become 3, 2, 1, 4, 5. So having number 1 never getting lower, that's not going to work. Anything along these lines is not going to work. All right, what about the following? The number from the bottom that are correct So I look at how many numbers on the bottom are correct. So if I have the numbers 1, 2, 3, 4, 5, if 5 is on the bottom, that's correct. So if I look at 1, well, I won't do 1, 4, 1, 2, 3, 5, I would say only one thing is correct, the 5 on the bottom. If I had 3, 2, 1, 4, 5, now I would have two things correct. What if the number of things on the bottom never goes down that are correct? Could that help? If it was strictly increasing, we'd be done. Right? If it was strictly increasing, we'd be fine. Once I get something on the bottom that's correct, it reduces to a smaller problem. What was the suggestion from class? Induction, right? So this would allow us to use induction. Unfortunately, is it possible that the number of numbers on the bottom is not strictly increasing? Yeah, we saw an example a moment ago where when we did it once, we still only had one number on the bottom correct. So if this is going to be useful, we're going to have to do more work on that. Yes?
If you have, like, when you have 5 on the bottom and all the numbers above it are less than 5,
Mhm.
5's never going to move.
Correct. And then by induction now we've reduced it to 4 problems. To the problem n equals 4. Exactly. And so the hope is that maybe we can do this by induction. That once we get a number on the bottom that's correct, it's never going to move.
It doesn't have to be correct, it just has to be.
Well, the only way it's not going to move is that if all the numbers above it are smaller than it, which means it has to be the largest number.
Or it at least has to be, like.
I mean, what we could have is if we have n numbers, if there is some k such that in the first k we have the first k numbers, we win. The last ones don't have to be in correct order. If we got into a configuration like this, so we could look at every time we iterate, how many of the numbers in the first k are correct. Do we have something like that where as time passes, we're doing better and better? Now what's interesting is after we iterate at least once, the 4 is put into the correct place. I'm sorry, the 2 is put into the correct place, which is good, but then when we iterate again, the 2 does not have to stay in the correct place, but something else goes into the correct place. So every time we iterate, what can we say?
One thing's going into the correct place.
So at least one thing is going into the correct place. Is it possible that every time we iterate, we have at least as many correct as before, or could the number of things that are correct go down? So here we had only the 5 was correct, and now we got the 5 and the 2 were correct, and then we got the 5, the 4, and the 1 were correct. Could that be an invariant or a monoinvariant? Is it possible to have something so if we iterate, we actually have fewer correct after an iteration than when we started? So again, to me, more important than solving this problem is trying to think how you would reach the monoinvariant. I don't know the monoinvariant for this problem. This is where you guys have to really think, oh, it's going to be a painful class. Do you think that the number of correct is non-decreasing? Or can you give me a configuration where if I iterate, if I go forward one step in time, I now have fewer correct than when I started? What do you think? So let's try, I have a 5 here. Let's put a 4 here. So when I move the 4 is going to go into the right spot. If I go 2, 3, 1, when I iterate, I now go to 5, 4, 2, 3, 1. All right, so let me just change it a little bit. Let me change the 1 and the 5. I'll put a 5 here and a 1 here. So 1 here, 5 here. How many were correct over here? 2. How many are correct here? 1. So the number of things in a correct spot can go down. So when you have problems like this, the best thing to do is to do lots of examples. Choose a couple of different sequences, order the numbers 1 through n, choose a couple of different values of n, and try to see what happens. For small values of n, you can do it exhaustively. If n is 3, not so bad. If n is 4, there's 24 possibilities. Of those 24 possibilities, a huge number of them are not bad. Which ones are not bad?
All the ones starting with 1.
All the ones starting with a 1 and
The ones starting with
well, if you start with a 1 or a 5, it's not bad. Right? Because if you start with a 5, you iterate once and the 5 is on the bottom. If you end with a 5, it's not bad. So you can eliminate a huge number of cases without too much trouble. So there's lots of ways to look at this. One way is to try to look and see, where does the largest number go as time passes? Does the largest number eventually fall to the bottom? Or what would it mean for the largest number never to fall to the bottom and the 1 never to fall to the top? So imagine that you never win. Do we all agree that if the largest number ever falls to the bottom or the top, we win? Because then we're done by induction. Right? If the largest number is at the top, it flips to the bottom, it stays there for all time. So if this doesn't eventually end with the number 1 on the top, the only way that can happen is 1 is never on the top, and the largest number is never on the top. All right, so now we've got to try to figure out, what do we want to study? What do we want to think of as the monoinvariant? And so coming back over here, one of the suggestions is a number other than 1 is only in the first position at most one time. Do we think that is true? If that were true, would that solve the problem? So we could use our monoinvariant could be the number of distinct numbers that have been first. And if we just wait long enough, eventually 1 has to have a turn. So what would it mean for a number to be in the first position twice? So we've got different permutations. So one way is to try to think, so what would it mean? So I'm permuting by doing very special permutations of flipping the first k, if k is my first number.
So consider your example.
Okay.
There, if you switch 3 and 1.
So now take 2, 4, 1, 3, 5.
Yeah, flip that around.
Okay, so that would become, the first I flip is 2, so it becomes 4, 2, 1, 3, 5. It's going to become 3, 1, 2, 4, 5. So 5 is just along for the ride. 2, 1, 3, and 2 is in the first position twice. Now, of course, what was nice here is the 1 is, but that's not always going to happen. So other thoughts on the monoinvariant? Yes?
I was thinking possibly saying numbers that are in position k that are greater than or equal to k.
Okay. Numbers in position k that are greater than or equal to k?
Yeah. If they're greater than they're not, then they're equal. They're also
So but when you say k, do you look at all of these at once, or do you just look at the one in the 2 spot?
sorry, what?
So are you saying, is this number greater than 1? Is this number greater than 2? Is this?
Yeah.
Okay, so for this one, if we look at it, 4 numbers. Oh, I'm sorry. 3. there would be two numbers that are greater than or equal to k. So 2 is greater than 1, 4 is greater than 2.
And 5 is greater than or equal.
Oh, we're doing greater than or equal to. So this would be 3. I mean, 5 is just along for the ride here today, at least for this example, right? 5 is doing nothing. We'll keep 5. So there are 3 numbers initially that are greater than or equal to k. Let's go over here. Greater than or equal to k, greater than or equal to k. So it's still 3 numbers. Now over here, 1 number, 3 numbers. 1 number, 2, 3, 4 numbers. Ah! So that one worked here. So if we think about what's going on, we're looking at numbers in position k that are greater than or equal to k. Clearly, when I flip things, anything below whatever this number is not going to be changed. But I'm not sure that this is going to work.
Like in that example, I think it drops you 4 to 3.
Yeah, I'm afraid that it's going to drop in one of these examples. In which example from right here?
Yeah.
All right, so here we would have 1, 2, 3. We would have 3 numbers.
You have 4 because 2 is.
Oh, sorry, 1, 2, 3. We'd have 4 numbers. And now if we come over here, 1, 2, 3 numbers. So unfortunately, that fails. Right? It is a great thing to try. You should still email me for a great class comment. One of the best letters of recommendation I ever wrote for a student was a small student of mine who had the wrong approach to solving a problem, but it was a damn fine wrong approach. And it could have worked. It just, when you did the calculations, the estimation did not work in the way we wanted. But he had a really good wrong idea. And that's important for stuff like this. You need to look at patterns, you need to try. The more things you look at, the better chance you have of seeing what's going on. We've still got 5 more minutes, and then this is going to end the monoinvariant unit. What else could we think of? I mean, we can start having more complex things, such as if I want to switch something here, I can keep track of how many numbers above the one above are correct, maybe?
Why did we throw out the number from the bottom that are correct?
Which one?
Or when we had the amount of numbers that are correct thrown out from the bottom as our amount?
Oh,
Why did we throw that out as an idea?
we have not thrown that out as an idea. We can't prove that it's strictly increasing. We know it's not decreasing. Because once you have things in the bottom that are correct, they can't go down because they will never move. So maybe that is the way to go. And so I'll put this up here. Number correct from bottom. So we can try to think, what would it mean for that never to increase?
It would mean that the n-1 spot was never, ever taken up by n-1. Which means that.
Are you talking about for this particular one where we had 5?
For example,
Yeah.
4 would never be in the 4 spot, which would mean that 4 would never be in the 1 spot. Which implies kind of like 3 would never be in the 3 spot.
Right, so can we somehow squeeze this and make this work? So let's start off with the simple case. Let's assume n is not in the nth spot, or the first spot. Because once we get the n in the last spot or the first spot, we're done by induction. So we'll try to make this idea work. So assume n never in first or last. So here's the last, here's the first. And because n is never in the first or the last, the n is never lower than n-1. So whatever's in the last position is stuck in the last position by itself and is never accessed. So how can we use this to help us? Induction. So now
Because now it reduces to a split case, basically.
the only difficulty is it's not quite the same case because the amount we shuffle by, the amount we flip by is going to depend on the number. And it's not that we now have the numbers 1 through n minus 1. We have n minus 1 of the numbers 1 through n.
What about sort of an expected value argument that the sum x1 minus 1 squared plus x2 minus 2 squared plus dot 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 x5 minus 5 squared?
All right, so x1 minus 1 squared plus
x2 minus 2 squared. This is very much just spitballing.
Okay, so we're looking at sums of squares, okay. How does this help us?
Sort of in general, you would expect things to get fairly close to their correct order. And so you'd expect this sum to either decrease or stay the same.
Okay, so the question is, have you done some calculations to see if this is always non-increasing?
I've done a few examples. It seems reasonable.
So even in the stuff like this, because again, when you're doing the flips, it's only the stuff in the beginning that matters. The stuff later on doesn't matter.
Yeah.
Oh, no thoughts, okay.
Well, if something's in its correct spot, it contributes a sum of 0.
It contributes a sum of 0. But we saw that there was an example where we had a lot of things in the correct spot, and then there was a lot of things that were moved. But it's worse to be far away than to just be a little bit away.
Yeah.
And so here, this could be a good thing to pursue. If n can never go below n minus 1, we've got to have a bunch of things above it. And then you could ask maybe, what's the furthest down n gets? Imagine n gets down to here. Maybe we can somehow do this by an induction, do some kind of minimality argument. Yes?
Can we argue that n minus 1 must be above n, because if n minus 1 is below n,
Good.
without n and n minus 1.
Okay, so now we know we have to have n minus 1 up and through here. We have something down here. I like that.
If n minus 1 is somewhere above there, then it's going to eventually get to the first position, and if it doesn't, then n minus 2 will eventually get to the, does that make sense? You can kind of narrow it that way.
Well, maybe n is hopping around and through here as well. And maybe n minus 1 settles down in here.
Well, no, so I'm saying like if n minus 1, like apply this exact same argument.
Right.
To a smaller.
The only problem about applying it to a smaller is that we don't have the numbers 1 through n minus 2 or 1 through n minus 1.
Yeah.
But I think there's a chance that that could work. I think there's a real chance that that argument would work for something like this. And so maybe we look at the lowest n gets as we iterate. Or maybe the highest n gets as we iterate. You know, maybe if n never gets below a certain point, do we somehow eventually find some configuration that pushes it further down? All right, so this is a good place to stop. I will let you think about this. I will think some more about this and send an email for people who are interested in terms of how to solve it. We are now ready to choose new topics.